Welcome back to Math 168. I'm Professor Robert Needing, and today we're covering section 3.3. We're going to be constructing bootstrap confidence intervals, and we're going to be using some technology in order to do that. So a couple of things: you want to have availability for stat key, and at the same time, the handout for 3.3. So let's see what we can actually do in this particular section. So our basic layout is we're going to do some bootstrap sampling. We're going to discuss the bootstrap sample and what a bootstrap sample actually is. We're going to look at the bootstrap distribution. We're going to calculate the standard error from the bootstrap, and we are going to make a 95% confidence interval level using the standard error from the bootstrap distribution. Hold on to your hats. Here we go. So in summary from section 3.2, to create a plausible range of values for a parameter, remember a parameter refers to a population, we take many samples from the population, and we compute the statistic from each sample. We compute the standard error as the standard deviation for all of these statistics, and we use the stat to take the statistic plus or minus 2 times the standard error. However, though, when we talk about this many random samples from the population, the problem is that we actually only have one sample. When we go to a population and we pull from that population, we get a sampling, and then we're pretty much done. We're moving on. We're going on to other stuff. But what we really need is many samples from that population. We can't actually get them. So that's where bootstrapping is going to come in. So this bootstrapping design is kind of like this. So pretend that we have one Reese's Pieces sample. So we go into some Reese's Pieces, and of n size 100, we pull out 100 Reese's Pieces, and we get 52 of them to be orange. So the p-hat value for this would be 52 over 100, or 0.52 would be our statistic, because we have this one sample. Now, in actuality, what we'd really like to do is we really have to go back in and grab another 100 and test them. And we'd like to grab another 100 and test them, and grab another 100 and test them. But if we keep doing that, all of the product's going to be gone. We're going to be sampling all of the product, and there'll be no product to sell. So the manufacturer's not going to be very happy for us pulling a statistical analysis like that. So what we need to do is we need to work with the 100 that we have in the 0.52 or 52 out of 100 proportion that we have, p-hat value that we have, and we need to be able to reproduce that, if you will. So what we're looking to determine is where might the true p-value be for all of the population. And it says, imagine the population is many copies of the original sample. Okay, many copies of the original sample. So what do we mean by that? So imagine this. So we take and I'm going to actually switch over here, and I'm going to kind of draw it a little bit. So let's assume that we pull this population. So here's the population of all the Reese's Pieces. Okay, this is all the Reese's Pieces known to man in existence currently right now. We just pulled out of there a statistic of N100. So we reached in and grabbed 100 of them. And from that N100, we got a p-hat value of 52 or 0.52 orange. 0.52 orange. Okay, so let's kind of think about that as a new population, if you will. Okay, this is my new population, because I don't get to go back and get any more. I'm done. This is all they're going to give me. But I really want to say, hey, do you think that 52% of these are orange based on the 52 that I got when I just yanked 100 out of here? Let's say there's billions of them in here. Okay, so here's what I'm going to do. I'm going to put all 100 of those items in here. So there's 100 of these original 100. I dumped them all back in again. And I reach back in again, and I take another p-hat value. Now remember, when I reach back up in here to these 100, I'm only going to grab a certain number of them. So maybe this time I'm going to grab n equal 10. I'm going to reach up in, I'm going to get 10 out of those 100. I'm going to get a sample. And then I'm going to do it again. I'm going to reach up in, I'm going to get another p-hat. So I'm going to throw them all back in again. So I take these 10, I record that number, I throw them back in, and I get a number. and I do it again, and I do it again, and I do it again, and I do it again. So bootstrapping is kind of that very same thing, that we take some sample that we have, we turn it into a new population, if you will, and from it, we take samples from it. We treat it like it's a population and we pull a sample statistic away from it. And that's really the art of bootstrapping. It's super simple, but yet at the same time, it's super complex. Why didn't we do this years and years and years ago? So we sample with replacement, and it says to simulate a sample distribution, we just take repeated random samples from this population and we make up many, many, many copies of the same sample. Now we have to follow some practices and some things to keep it statistically sound, and we'll cover those in a second. In practice, we can't actually make infinite copies of the sample. It says in practice, but we can do this with sampling if we have the units that are going to be selected more than once. Think about it kind of like this. So let's say, suppose we have a random sample of 6 people. The original sample on the left-hand side over here, these are the original 6 that we drew. And let's just say I just reach in and I draw one of these out. Boom, it was black stick guy here. And I put him back. And then I reach in again and I draw out this guy, big round guy. I pull him out. And I throw him back. I reach back in again. Oh, look, I got black stick guy again. Remember, every time I draw one, I put it back in. And I draw one and I put it back in. And I draw one. I can do this over and over and over and over and over and over. I can do this as many times as I want until I feel good about the resampling that I'm taking over and over. And remember, this original sample should be indicative of what happens inside of the true population parameter if I followed all of the rules of engagement that I did, if my sample was random, and if I didn't use bias when I took my sample. It says a simulated population to sample from. So really what I'm creating is I'm creating a population that I can go in and then sample from. A bootstrap sample does that very same thing. It samples with replacement. That's a key term for you. With replacement from the original sample. Remember, we're treating that original sample like it's the new population. Using the same sample size. That's big. Same sample size. So if you started with 6, you got to create 6 more, and then 6 more, and then 6 more, and then 6 more, and then 6 more. It's always going to be in that bootstrap sample of 6. So here's some questions, and here's some bootstrapping, and we have to follow the design of what we're doing, if you will, here. So we have an original bootstrap sample, has 18, 19, 19, 20, and 21. Those are the original values. And the answers are yes or no. Can this be a plausible bootstrap sample? So I go to the first one, 18, 19, 20, 21, 22. It cannot be an original bootstrap sample. Why can't it be an original bootstrap sample? Well, because 22 somehow wound up in the bootstrap right here, right there. I'm going to have to underline it because it's not a piece of text. 22 was not in the original bootstrap sample. It was nowhere. Remember, it has to come from here. And if 22 is not here, then 22 doesn't get to be down here. Letter B, your original sample is 18, 19, 20, 20. It looks like the same stuff. Is the following possible bootstrap? I have an 18, I have a 19, I have a 20, I have a 21. All the numbers you see are in above, but the answer is still no. Why not? And because the sample size is not the same. Meaning there were only 4 in the sample taken, and there were 5 in the original. The bootstrap sample has to be of same size and drawn from the same numbers. Letter C. We have an 18, an 18, a 19, a 20, and a 21. We have 5 things, n equal 5, and they all came from there. We finally have a winner, and the answer is yes, this can be a bootstrap sample. A bootstrap sample is a random sample taken with replacement from the original. So we want replacement from the original sample of the same sample size. Those are the 2 key pieces of orientation you have to have. A bootstrap statistic is the statistic computed on a bootstrap sample. When we take a bootstrap statistic, it comes from a bootstrap sample. Again, if we go back to mine, I went into here. This was my bootstrap statistic, and this bootstrap statistic came from that bootstrap sample. I sampled 10, I sampled 10, I sampled 10. I always sample 10 because remember, when I bootstrap, I have to sample of same size. A bootstrap distribution, completely different. A bootstrap distribution is the distribution of many bootstrap statistics. We did not yet do a distribution, but if we take all of these numbers and we create a distribution with all these dots stand for one of these up here, all these p hats are being put down here into a data plot. And I'm making a dot plot, and I'm making a distribution, and this is the distribution of my many, 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 many samples. That is what it will look like when we do a bootstrap distribution. So in a picture, I don't think nearly as good as mine, but who knows, maybe it is kind of closer. We start with an original sample here, and we pull a sample statistic. So maybe 0.52. Remember, we pulled 0.52 for the Reese's. Then from the original sample, we go grab a bootstrap and a bootstrap and another, many, 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 many times. And each one of those, we pull a statistic. Then we take all the statistics and we put them into a bootstrap distribution. I don't know, right here, I think I should have some kind of poll that says whose picture is better, my picture or the college picture. I think we can all agree mine's a little bit better than theirs. So how do we run a bootstrap distribution from StatKey? And what does it mean when we get it? Okay, well, let's take a look at the picture, then we'll go run it. So first of all, a bootstrap distribution will be in the center box here. This will be the actual distribution of all of the many, 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 many samples that we take. The standard error is circled in red right here. You'll see the standard error populated right here. We'll need that standard error to do our confidence interval level. Remember, statistic plus or minus 2 times the standard error. Over here on the right-hand side will be the original sample proportion right there. So we'll take this proportion of 0.520 and we'll plus or minus 2 standard errors right here to get a CI. So how do we do that in actual StatKey? Okay, well, first of all, we go StatKey. Bootstrap is in the center. That's where we want to be. Let's say that we're dealing with a single mean right now. In a single mean, we're going to want to, first of all, look over here to the right. Original sample. The original sample has a 15.98 mean, and it's got a standard deviation of 11.1114. Okay, that's the original. If I do one single bootstrap, I'm going to reach into this 25 right here, and I'm going to pull out a sample. Boom. 25 in here. I went in and I pulled out 25 more, and I got them. Now, how come they're all not the same? People always ask me, well, if they're the original 25, it's going to be the same number. No. Remember what happens is I pull one number out, I put it back in. I pull one number out, I pull it back in. I got to do that 25 times. So in essence, it could happen that I pull the same number out 25 times. I am not going to get necessarily all 25 of these original dots. I'm going to get 25 dots, but they're all going to come from this pool over and over and over again. When I did this one, I got 18.392, and it plotted it right there. Now, if I do that 1,000 times, it reaches back in, and it does that 25 times 1,000. It just did that 25,000 times, and it dotted them down here. And you can see my standard error now is 2.253, and I am working at 15.98-ish on my center here. If I run this a couple more times, look at the bottom number. Look at how see how it changes? It always will, just a little bit. Remember, this was the original sample. This is what we think is going to happen to the population. Remember, what we're really looking at is we're looking for the standard error. What is the standard error going to be? Because we're going to apply the standard error to the original sampling of 15.98. This just tells you what Bootstrap really infers and where they came up with the name. More important to me that you have this yellow box in hand. A Bootstrap statistics are the original sample statistic as the original sample statistic is to the population parameter. The bootstrap is highly related to the sample statistic. It's going to treat it, the sample statistic, like it's a little population. The same way the original sample seems to infer things back to the population parameter. The center, the sampling distribution is centered around the population parameter. That's important. And we'll say that one a couple again here. That the sampling distribution is centered around the population parameter. If I go back here, this sampling distribution is centered around what we believe is the population parameter, 15.993. The bootstrap distribution is centered around the sample statistic. So now we have two different things here. We have, and let's make sure we define clearly and make sure that the words come out right and make sure I get them right for you. So when we talk about a sampling distribution, okay, it's going to be around a population parameter because we're going to take many samples from there. When I do the bootstrapping, I'm centering up on the statistic. The statistic here, remember, this is the mini population. And when I center up here, I'm centering up around this data. But remember, this distribution, this bootstrap distribution is to this sample as this sample is to the population. We're going to infer a value, and I'll just show, we're going to infer a confidence interval level here that can then be applied to the sample statistic that we can apply back to the population parameter. Luckily, we don't care about center. We only care about variability, and that's what I just said. Standard error is variability. They are the same thing. Maybe we want to write in there, right next to here, standard error. The variability of the bootstrap statistic is similar to the variability of the sample statistic. The standard error, there it is, the standard error of the statistic can be estimated using the standard deviation of the bootstrap distribution. And where do we see that? We see that right here. The standard error right here is going to be our applicable design in order to get this confidence interval level. And when I click this two tail, that shows me the plausible confidence interval level for this bootstrap distribution, 11.984 to 20.560 on a 95%. If I need to change that 95%, we'll talk about changing that later. So here's a nice kind of big picture, right? So we go to a sample and we pull out many bootstrap samples. We take those many bootstrap samples and we put them into a big old distribution chart. So we run thousands of times in there. From there, we calculate a standard error because we see that standard error calculation in the bootstrap distribution. From there, we take the 95% CI calculation, which means the measurement of error equals 2 times the standard error. Now that we know the measurement of error, we take the original statistic and we plus or minus the measurement of error. This will give me the confidence interval level. Question number 11. In a random sample of 1,000 people, 382 people agree, 578 people disagree, and 40 are undecided. Estimate the standard error. Round your answer to 3 decimal places. Okay, so we're using first of all, and it gives you a couple hints, and you always want to read the couple hints if you need to here. First of all, it tells you use stat keys CI for single proportion. Well, it has to be a single proportion because we're talking about a certain number of people out of a certain number of people. And right now we're interested in 382 out of 1,000. So let's go to here. Let's go to stat key. Let's go to single proportion. Now we're going to have to edit our data because, look, it's 0.520. It's got some kind of crazy mixed nut coconut thing up here. So we hit enter. We put 382 in for the count. We put 1,000 in for the sample size, and we get 0.382. That's what we wanted right there. Okay, that's a first step. Then let's generate 1,000 samples. Let's wait for that. Okay, so now that we have that 1,000 samples, now I see that I have a standard error right here of 0.016. That 0.016 is what I'm looking for. So let's go back to the original question, and it says, what is the standard error? Standard error, 0.016. Got it. Find the 95% confidence interval level. Okay, so how are we going to actually find that confidence interval level? Well, we're going to take the statistic 0.382, and then we're going to add and we're going to subtract 2 times the standard error. And the standard error is 0.016. That's how we're going to make our calculation for the confidence interval level. So the bottom end is going to be 0.350. It's the minus value. And the plus value is going to be 0.414. There's my CI for a 382 out of 1,000 on a 95% CI. It says, what about other parameters? Well, it turns out that we can really use this for any parameter that we want. We can use it for proportion, a difference in means, proportions, standard deviations, correlations. It will work for anything that we have to do. We just have to recalculate many samples. The magic of bootstrapping is that it works around any statistic. If we have sample data, we can use bootstrapping to create, and I'm going to highlight this here, a 95% CI. If we're not calculating a 95% CI, we have to do things just a little bit differently, and we'll do that also. In a recent study, examine the relationship between football playing and the hippocampal volume in UL in the brain. We use N25 participants in the control group to estimate the average brain hippocampal volume for all non-playing. So notice those words there that are being used, and I want to underline some stuff for you here. So first of all, we're using 25 participants, that's our sample, in order to make a claim on the population of all non-playing football people. The original football data is shown. Okay, well, remember, the original football data was only 25 things. I got 25 things. So the original football data is in the plot II, this one here. The bootstrap distribution. Okay, well, when I do the bootstrap distribution, remember, it was the one where I did many things. I never had all those many things. It's an I. The correct notation for the sample mean hippocampal. Well, I'm going to have a hard time with this, but I'm going to try. It's X bar. That wasn't too bad, I guess. X bar. Estimate the sample mean. All right, well, when I go to the sample mean, I got to kind of look in the middle. My estimate in the sample mean to the nearest integer, I'm going to come right down through the middle right here, and it appears that it's going to be 7,600 because that's the number closest to where I'm coming down through. So 7,600 is my estimation. Estimate the standard error if we use the sample mean to estimate. Okay, so let me change colors here. Remember, there's 2 standard errors on each side. So if 7,600 is the center, then when I move, let me grab a different color here. Let's grab this one. Then this would be 1 standard error, and this would be 2 standard errors. So it looks like I went from 7,600 to 7,800 to 8,000. Same deal going down to 74 and down to 72. So my best case guess at the estimation using an integer is 200. What do we got here? A random sample of 20 automobiles, we record the value of the model of a new car as the value after the car has been driven 10 miles. Yeah, little known fact, you buy a brand new car, you drive it off the lot, you turn around at McDonald's and you come back, and guess what? It's a used car. 3 differences, the differences, between these two is measured as the depreciation of the car by just driving it off the lot. The depreciation values from our 20 sample automobiles can be found in the dataset car depreciation. Okay, and they give us some links if we need to, but I have the links open already. Round your answer to the nearest integer. Find the mean and the standard deviation of the depreciation amounts for the car. Okay, so first of all, we need to go find this data. So we're talking about mean values, Bootstrap, stat key. I'm going to the center for mean. It wasn't difference in means, it was a single mean. Over here on the left-hand side, I'm going to find car depreciation. It's right here. Car depreciation. Now, the first question was, what is the mean and the standard deviation of the original sample? I don't need to run anything. Those are right here. The mean is 2,356 when rounded, and the standard deviation looks like it's going to be 858. So I'm going to go back to here and do a little typing here. So my mean value was 2,356, and everybody should have the same number for that. And the standard deviation was 858. Those were consistently the same because they were pulled from the original sample. Now it says use stat key to create a bootstrap distribution and then give us a center and a standard error. Okay, so let's go back here. Let's run 1,000 of these. And maybe if you want to run more, but I ran 1,000. And I get a mean of 2,349. Now watch what happens if I reset and I run again. 2,358, that'd be 2,359, but watch if I run a couple more. I kind of like to run about 10,000 samples because I think 10,000 gives me a good idea. Oops, I ran 11,000 actually, not going to hurt. 2,352. So for me, I'm going to write down, because I like 10,000 better than that, I'm going to write 2,352. Now, we know we have a plus or minus to this number when you're entering yours, because yours could be different. You could be running it right now going, but needing, mine says 2,353. It's okay. It'll be all right. Now, because of my 2,352, though, I have a standard error of 188 is where I have, because I'm going to round up to 188. So in mine, 188. That could be completely different for you. If you ran less, this would be a greater number. If you ran more, this would be a lesser number. If we tell you how many samples to run, then run those many samples. If it doesn't tell you how many samples to run, I'm recommending 10,000. So use the standard error to obtain the bootstrap distribution of this confidence interval level. Okay, so I have to use my numbers, and I'm going to open up both pieces. I'm going to open up both screens here. So give me one little second. And Windows over, and I need to grab here. So my original sample that I have is 2,352. My 2,352 is then going to add and subtract a confidence interval level of 2 times 188. So if I take 2,352 and I subtract 2 times 188, I'll start with the minus 1976. And if I take that very same line and I now come back and I add into it, oops, almost there, 2,728. There's my 95% CI for my question. In summary, to generate a Bootstrap sample just for a distribution, we would generate Bootstrap samples by sampling with replacement. Notice that's blue and highlighted there for you. With replacement many times from the original sample using the same sample. We would compute the statistic of interest, a Bootstrap sample statistic for each of these. We would collect the Bootstrap samples, and then we would create a distribution if it was bell-shaped and symmetrical by taking the statistic and adding and subtracting 2 times the standard error. When we come back, we will be on section 3.4, and it'll be a great time. I guarantee it. I'll see you then.